additional work.
Yeah.
In a hospital, right? Better.
High patients? Sorry, I do not follow.
The arrival patient in the hospital is not stationary.
Yeah. Their complexity, you mean, increases and
Time during arrival.
oh yeah,
Yeah.
time. Yeah, that's something we are interested in. So maybe it's good idea to include time varying, but for now, since I'm developing something, I'm in process preliminary work for my PhD project. So maybe in future I will be, because this is something that was suggested by my supervisor, and maybe we will include this in future. Maybe. Yeah, yeah.
I have a question actually.
Yeah.
Which is a situation, so if I've understood correctly, the B represents a number of ward beds in the hospital, correct?
Yeah.
Not beds in the
Yeah.
emergency department. And N minus B represents the waiting area
Waiting
trying
area.
to get access to emergency before. So in between, we now have the number of emergency doctors who are selecting the patients, right? So, well, picking up on Ivo was saying, at certain times of the day, especially late in the afternoon, leading into the night, and then the early morning, things get really congested, and the system is more or less operating at about 100%. So there could be a component of delay there, significant delay. Have you any thoughts about incorporating?
Yeah, actually, we did not consider in our analysis, but that's a good suggestion from you. I really appreciate. Because we are considering only the constant rates based on days. So if we consider 24 hours, that means we are including, I mean, all of the odds. So that's something I think we can include if we consider the time depending arrival rates. Maybe we'll have a look on that. Yeah, good suggestion.
Any other questions? Okay, is Haoran here? Okay, good.
Thank you.
So while we're waiting on suspension, of course, the Haoran is a school of justice at Yat-sen University. But this is based on work that he's been doing with Qiming and Lisha.
Thank you, Professor. Hello, everyone. I'm Haoran Wu from Yat-sen University. Today, I'm going to talk about the queuing system with correlated interarrival and service times and general abandonment. Like Professor Stanford mentioned, this is joint work with Dr. Qiming He and Dr. Li Xia. Here is the outline of my presentation. First, I'm going to briefly introduce the background and the motivation of this model, and then I will give you the formal definition. After that, I will talk about the analytic framework. Basically, we analyze this model based on existing methods like the age process and the Markov modulated flow process. And we will show you what kind of performance metric we obtained in this model and give you a very simple numerical example. And last, I'll conclude our contribution and the future direction. First, the queues with correlated arrival and service process have been investigated maybe 50 years ago, and but it has never been a hot topic in the past. And unfortunately, there's some interesting research and empirical evidence in the literature. One is by our next keynote speaker. I think 20 years ago, they using the data from telecommunication and discover the dependency between arrival and service time. And then another one is also about our colleagues, Boiler and Bean. Last year in healthcare system, they also found this dependency between interarrival time and service time. On the other hand, the queues with abandonment is a really hot topic in the past, like maybe 20 years ago. In the call center, there are a lot of papers invested abandonment in the system. And in the last 2 decades, maybe many in healthcare, they call it live without being seen in, like, for example, in the emergency department. So I think Abdul just give a very perfect example. If there is a busty arrival in the emergency department at a short time, and certainly the patient would need to wait longer, and eventually their health condition will deteriorate, and eventually they may need a longer service time. So in this sense, it explains those kind of dependency between arrival and service process. And so in this paper, our goal is to provide a unified approach to accommodate both correlation and the general abandonment distribution. And at the same time, we want to get how the dependency structure, or more specifically the correlation coefficient, will affect the performance metrics. So that's the motivation. In terms of literature, for the correlated queues, we only found a few papers which assume a direct dependency between interarrival time and service time. Although there are a lot of people would assume there are maybe some kind of common background process to control both the arrival and the service, but only a few of them to investigate the direct dependency. And we divided into 2 streams. One is at the early stage, they would assume there's some kind of proportional relationship between interarrival time and the service time. And the mainstream is to use this bivariate distribution to model the correlation. Maybe also they may use different bivariate distributions. So here the highlight part is those literature related to our community, MEM, like Alpha in 2021, he investigated a discrete time queuing system with correlated interarrival and service time. And Badila and our project group, we also invested this kind of correlated queues 2 years ago by using this bivariate phase-time distribution. And this bivariate phase-time distribution is mainly based on the following 2 papers. One is by Blood and Nielsen in 2010. Another one is Professor He in 2012. Oh, so this part is about the correlated queues. On the other hand, for the abandonment queues, there are abandonment papers. So we only list a number of them in terms of Matrix-Analytic methods. Like again, there are two categories. One is with the assumption of constant abandonment time. So there are a number of specific models like MAP, MK, and MPHK, and so on. And for the random abandonment assumption, again, there are a lot of papers. What I want to emphasize here is the one by Haoran and Van Hart in 2012. They used this Markov module through the flow process. So basically, we follow their idea to analyze queuing system with abandonment. And 5 years ago, when I was a PhD student here, we already did a series of work about the queuing system with abandonment. And this is one of them. And to the best of our knowledge, we couldn't find existing literature about queuing system with both correlated arrival and service system, service process, and abandonment. So that's why we thought maybe this is an interesting topic to investigate. Okay, then I will give you the formal definition of our model. For the correlation part, since we are going to introduce the bivariate phase-time distribution, so I will spend maybe next few pages to introduce this part. And for all other components of the system, like the arrival, the service discipline, the service time, are all standard. Like we assume there is a person arrival process, and the service discipline is first come, first serve, and the service time is exponential distribution. For the abandonment time, we assume there is a general discrete distribution. So we assume the patient's threshold is tau is Ln with probability eta, and so it's a general discrete distribution. Therefore, the stability condition is eta capital N times rho less than 1, which means for those customers with infinite patient's threshold, their arrival rate should less than the service rate. Otherwise, the Q-length can go to infinity. So that's the definition. Then I will introduce how we model the correlation part. So here is the definition of bivariate phase distribution. I think yesterday Mitra mentioned this multivariate phase distribution. So here we can simply think it as we further divided the transient states of the Markov chain into two subsets. So random variable X records the total time spent in the first M states 1 to M, and another random variable Y records the total time spent in the next M, the M plus 1 all the way to 2M, and eventually, of course, they go to the absorption states. Therefore, we have two random variables, and their correlation is somehow determined by this block D. So how to determine their correlation is mainly based on this block D. Here is a simple example. Like here, X records the time spent in state 1, 2, 3, and the random variable Y records time spent in states 4, 5, 6, and eventually they go to the absorption state 7. And once we have the bivariate phase distribution defined, we can derive the joint LS transform, and eventually we can calculate their correlation coefficient based on those blocks we just used. And but in this presentation, we focus on this MM1 plus GIQ. So we need additional assumptions about those blocks to make sure those two random variables are marginal exponential distributions. So we need to add a further assumption about those blocks D0, D1, and S0. First, we want to make sure this D1 over lambda is a doubly stochastic matrix. And further, we followed the construction by Brother and Nielsen in 2010. So we want this S0 and the D0 have those kind of form. But this way, we have a bivariate exponential distribution. And further, if this D1 is an identity matrix, we have the minimal value of the correlation coefficient. And if it's anti-identity matrix, we get the max value of the correlation coefficient. And from this diagram, we can see the range with different value of the order of the construction. Basically, the value of M, we can see the change of the range of the correlation coefficient. And of course, if we increase in the value of M, and it goes to infinity, we can get the upper bound and the lower bound of the bivariate exponential distribution. And further, if we want to arbitrarily set the value of the correlation coefficient, we can just use this formula to combine the identity matrix and anti-identity matrix. And by this way, we can numerically to show how the correlation coefficient impact the performance metrics. And later in the numerical example, I will give you some graphs. So that's the model definition part. And next I will discuss how we analyze this model. First, we need to define the age process of this system. So the age is we define it as the age of the customer in service or at the head of the queue at the time t if the queue is not empty. Otherwise, we say the age is 0. So in this diagram, let me show how we track the evolving of the age. At the beginning, we assume this is an empty system, and then we have the first customer arrive. Once this customer arrives, the age of the system increasing linearly at rate 1 until the customer departs the system, and then with the age drop to 0 again, and remain there for a while until the next customer arrives. We see the blue customer, and again, it increases linearly at the rate of 1. But here, even when this blue customer is still getting service at the server, and the next customer arrived, but we still track the age of the first customer. And we don't track the age of the next one until the first customer, the blue one, complete his or her her service, and then we jump down to the age of the next customer, and then the heat of this jump is exactly the interval time. So that's how we use the age process to track the evolving of the system. And why we need to use this age process is because of the correlation. If we want to use QBD, then we need to track the underlying phase of all customers in the system. And if the queue length gets bigger, then the system, the states of the system, the order of the system would be too large. So that's why we use this age process to only track the age and also the phase for the first customer only. That's the advantage of this age process. One of the reasons we use age process later. For the abandonment, again, I think this is a useful tool. Then we follow standard procedure to analyze this age process. Basically, we turn this age process to a MMFF process by adding fictitious period to turn those time jumps to linearly decreasing periods, and then we can analyze the MMFF process. I think here is the formal definition of this.
Can you go back one slide, please?
Sure.
So the jumps down which don't go to 0.
If this is the only customer in the system, of course, after he completed his service, then the system is empty, and then they go down to 0. Otherwise, they go to the age of next customer.
Yes. So if you look at the second example, the jump,
right?
the size of this jump is essentially
the interval time.
Yes, but the distribution is uniform, right? It's not exponential because it's kind of conditional on one arrival during the stop.
Here, is it exponential because
given that you have an exponential condition, exponential distribution, but if you know that it's not that the customer was in line, it means that it arrived sort of during my last service time, essentially.
I think it depends on how you define the correlation. In this model, we assume the service time depends on the interval of this customer and the previous one. So in this way, the arrival is independent of service, right? Right. So that's why at this point, when they go down jump, I think it's still exponential. That's my understanding of this. Maybe we can talk about it later. Okay. All right. So here is the formal definition of MMFF process. So with this one, we can basically, I think yesterday a lot of speakers already mentioned this fluid process. So basically, this is a two-dimensional stochastic process. One is the fluid level, and another one is the underlying Markov chain, and the fluid going up and down, driven by the underlying the state of the underlying Markov chain. And in our QA model, we have this Q built by those blocks defined in our QA model. So this the Q looks like this. And with this defined, then we have a well-defined MMF process. And then we can analyze it to get the joint station distribution of this MMF process. And the result is mainly based on those basic matrix of this process, like this kappa and the psi. And again, we can follow the standard procedure by censoring, and we will get the joint stationary distribution of the age process of this one. But so far, we haven't discussed abandonment. So later, next, we need use a little bit of complicated process called multi-layer MMFF process. The main purpose is to incorporate those abandonment time distribution. So the difference between this one and the standard MMF process is here we have level dependent Markov chain, underlying Markov chain, and for each layer we have its own underlying Markov chain Qn, and here we need to incorporate the abandonment time distribution eta 1 all the way to eta n into those transition blocks to model the abandonment time. So that's the main part of this multi-layer MMFF process, and eventually we can get the joint stationary distribution of the age process. And with this result, the joint stationary age process, then we can derive all kinds of built-in performance. There are three sets: customer abandonment probabilities, sojourn time distribution, and equivalence distributions. So first is the customer abandonment probabilities. So we can have the probability that customer receive completed service, and the abandonment probability of customers already in service, and the abandonment probability of those customers before entering the server. Similarly, for the sojourn time distribution, we can also get the distribution of the sojourn time of those customers who received completed service, and the sojourn time of customer, those customers abandon the system when they are in the server, and those sojourn of those customers abandon the system before entering the server. That's the sojourn time distributions. And the last is the Q-length distribution. Here I only present the mean Q-length, which is derived based on the moment generation function. And all the calculations, I think, is in closed form. We can get the exact results. Then I will give you a simple example. Here we have a correlated MM1 plus GIQ, and the arrival rate is 1.5, service rate is 2, and we assume the abandonment distribution looks like this. And for comparison, we will use different construction of D1 to compare their performance. And here is the result. If D1 is 1.5 times the identity matrix, which means it has the minimal value of the correlation coefficient, and another one is 1.5 times the anti-identity matrix, and the last one 1.5 E times E prime over 5 model the system without correlation. That is the standard model, and we find for some performance, so one with the largest correlation coefficient has the best performance, and for some metric like the service probability, the one without correlation has the best performance. And this diagram is the sojourn time density function with different construction of D1. And the interesting result is we further to draw those performance in terms of the different value of the correlation coefficient, and then we discuss some kind of non-monotone effect on those performance. In the existing literature about a queuing system without abandonment, they always observe monotone effect of the correlation coefficient on those performance, especially the queue length, the mean queue length, and the mean waiting time or solution time. But in this abandonment queuing system, we found maybe because of the abandonment, there are some kind of non-monotone effect on the performance. That's from the numerical example we found effect. Last, let me wrap up my presentation. I think we have mainly two contributions. First, we developed a queuing system that incorporate both correlated inter-arrival and service time, along with general customer abandonment distribution. Second, we found this non-monotone relationship between correlation and performance metrics. In the future, I think first, we can easily extend this work to the system with space-time distribution, because those blocks, we add additional assumption to make sure they are expansion. Basically, we can just use space-time distribution to analyze. And second, we want to apply the system to as just some real-world applications, like in healthcare, in emergency department, something like that. And I think that's all of my presentation. Thank you very much.